So the other thing we talked about is there are a bunch of constants that you have to memorize. Most of the constants you have to memorize are for water only. So for example, the specific heat of water, the density of water. Most of the stuff this semester, I've said, okay, yeah, you got to memorize this, but it's for water. All right. Anything else I would give you, or I would give you a table to look it up. I don't expect you to know specific heats of random metals, for example. Okay. So first thing we're going to do, and this was one of the examples that was in the video. This is a very, very, very common example when introducing thermodynamics. So it was about the potato cannon. If you watch the video, you remember about it. So potato cannons, I'm sure you've seen them. They're just like those t-shirt cannons where it's closed at the one end, open at the other. You shoot the potato through it. So this problem here, I'm just going to review this really quickly because we went through this example I went through it in the integrity video. But what it says is the firing of a potato cannon provides a good example of the heat and work associated with a chemical reaction. In the potato cannon, a potato is stuffed into a long cylinder that is capped in one end and open on the other. Some kind of fuel is introduced under the potato at the capped end, usually through a small hole, and ignited. The potato shoots out of the cannon, sometimes flying hundreds of feet, and the cannon emits heat to the surroundings. If the burning of the fuel performs 855 joules of work on the potato and produces 1,422 joules of heat, what is the delta E for the burning of the fuel? So, yes, they actually, oh, that's funny. A potato cannon can be dangerous and should not be constructed without proper training and experience. I guess they don't want to be sued. Okay, at the top of page 373, there is table 9.1. Okay, this table is your new best friend for this part of the chapter. And the reason for that is the words used in these problems are going to tell you if your Q's and W's need to be positive or negative. Okay, so this particular example said the burning of the fuel, so the fuel produced 855 joules of work onto the potato, Okay, if you look at table 9.1 where it talks about work done onto the system, the potato is the system, and we'll talk about that in just 1 second. It's going to be positive W. Work, W. Okay? Then it says it produces 1,422 joules of heat. So it produces 1,422 joules of heat. So this is our Q. Okay? And so the question is it going to be negative or positive? Well, go back to table 9.1. The cannon, or the burning of the fuel, produces. That means the heat given off by the surroundings is equal to the amount of heat absorbed by the system. Okay? That whole energy lost, energy gain thing can't be created nor destroyed. It can just be changed from one thing to another. So if the heat, if you look at that table 9.1, it says for heat, it's a positive Q if the system gains thermal energy, and a negative Q if the system loses thermal energy. I'm on page 373. Sorry, page 373. Okay. All right. So if the burning of the fuel is 1,422 joules of heat, that's the fuel. Now let's talk about this in terms of system and surroundings. Here's my cannon. Okay, it's my little potato. And, sorry. So we'll just pretend this is outside, right? So here's person with the potato gun, okay? My wonderful drawing. So if we're talking about this, the potato, we could consider the system. We consider it the system because that's what we're looking at. The cannon, or the fuel in the cannon, is the surroundings, and everything else is the universe. Okay? So if heat is put into this potato, the amount of heat lost by the fuel is gained by the potato. It's equal numbers. And just like we said, remember we talked about bond energy, the amount of energy it takes to break a bond is the same amount of energy it takes to form that bond. Same concept. So what we know is that the surroundings produced 1422 joules of heat. That means, given this, the system must be 1422 as well. Okay? If the surrounding is losing, the system is gaining, and vice versa. Okay? So what we're going to say is delta E, which equals Q plus W, it's going to be negative 422 joules. Oh, sorry. Okay, negative 422 joules. Now, let's just go back to this really quickly. The potato is 855 joules positive. So what does that mean for the surroundings, the cannon? Okay. So when we do this, our math is just 2277 joules. Okay? That's delta E. I think we should do another one because wording is fun. Are you guys good? Can I change the page? Okay, I'll wait. I'll give you a minute. There's going to be a lot of opposites in this, so you have to be kind of really diligent about keeping track of what's what. One of the things I like to do with a lot of these problems is to just go off to the side and kind of write what I got. So Q for the system equals this, you know, W for the surroundings equals blah, whatever, just so I can keep straight in my head and then figure out kind of the positive, the negative, etc. Okay? All right, we good? Can I change it now? All right, so let's do another one. Let me just write this really quickly. Okay. This looks like a test question. I can tell you that right now. This is the type of question you'll see on a test. Okay. I told you that this chapter would be one of your most challenging this entire semester. And honestly, most of the reason it's this challenging is because of the wording. I'm pretty sure you guys can plug and chug for delta E equals Q plus W. The trick is figuring out what Q and W are and if they're positive or negative. And it's hard to figure that out based on the wording. So we're going to pick this problem apart before we even deal with numbers. All right? Okay, we good writing down? Anybody need another minute?
So is this considered like a hard problem?
No, this is considered a regular problem. Okay, we good? Okay. All right. Alrighty. So let's look at this. First things first. We've defined the system as the cylinder and the piston. Why we define it that way, who knows, doesn't matter. That's what you're told. That's the system. That means everything else is the surroundings. Okay? So when it says the system absorbs 559 joules, that's Q. The question is Q going to be positive or negative for the purposes of this problem?
Positive.
Why?
Because it absorbs it. The system is absorbing.
Okay, what's the rule? I'm not saying you're wrong, I'm just saying what's the rule?
The system gains thermal energy.
Okay, how'd you know that?
Because that's just the rule.
But you didn't know that, right? Say it again. The table, okay? Table 9.1, you need to know that. It's your new best friend. It clearly states if the system gains thermal energy, absorbs it, then it's going to be a positive Q. Okay? Now, I kind of ignore till I get to work. Okay. So it does, now the system does 488 joules of work. The rule is, back to the thing, if the work is done by the system, it's a negative W. Okay? So now we can ignore everything else and say delta E is equal to Q minus W. Why? Because I'm using a negative W. So I'm going to say 559 minus 488. And yes, it does matter if you put Q or W first. Keep it in order. Q, then W. Okay? All right. So doing the math, I've already done it. That's equal to 71 joules. Okay? Questions about this? Nothing?
So really and truly, you just gotta learn the words like absorb,
Yeah.
that's it.
Yeah, you're going to see things like absorbed, evolved, transferred. You know, if it tells you the system transfers heat, for example, I don't care where it transfers it to, if the system is transferring heat, that means it's losing heat. Okay? You got to kind of read between the lines a little bit. And then refer to this table. Okay? All right.
Why'd you write 11?
I wrote 71.
I thought it was part of this one.
No, it's not. Okay. now we're going to focus on that. This is specific heat. And delta T is T final minus T initial. Now, I really wish you guys would do this lab, but you don't, and I don't understand why. But one of the labs that you'll do in Chem 2 is the calorimeter lab. And so they're these styrofoam little containers with lids, and you can, in it, the first part of it is you'll have cold water, or, not cold, but like room temperature water in it, which you'll measure the temperature of. You will heat up a block of metal and heat it up for a certain amount of time, and you'll take that metal, put it into the calorimeter, quickly close the lid, and then record the temperature, and you know that you're at thermal equilibrium when the thermometer has stopped moving. And what that means is you can assume the final temperature of both the water and the metal is the same degree. All right. You can also assume that when you heat up your metal, if you put it in a test tube, put it in boiling water, 15, 20 minutes, whatever. When you do that, you can assume the temperature of the metal is equal to that of the boiling water. Okay? So there's a lot of different factors going on. But oftentimes we use that lab first to find the calorimeter constant. Then we use, once we have that calorimeter constant, then we use that same experiment to find out knowns and unknowns about things. Maybe we're looking for specific heat of a metal, of an unknown metal. Maybe we're looking for the initial temperatures, etc. It just depends on how we set it up that day. But it's all based in this. And when we do the calorimeter lab, you're going to have this for the water and also this same equation for the piece of metal, but you're going to set them equal to each other because, again, Q of A is equal to negative Q of B if we're talking about water and then putting something in the water, right? Or hot water being put into cold water or something like that. So they're equal to the negative of the other because whatever heat is lost from the metal and put into the water is equal to the amount the water is gaining from that metal, which seems like duh, that makes sense, right? But you just have to keep reminding yourself of this. So here's another problem, and this will look like, honestly, this is one of the most common questions we use on a test. I'm like, I can't talk and write, you guys. Okay. Now, on something like this on a test, I would give you the specific heat of copper. For now, the book, when it gives you these kind of problems, it assumes you're just going to look up the specific heat. So the specific heat of copper, where is it? Okay, that's the specific heat of copper. Also, keep in mind, if you ever are looking up these specific heats, make sure you're looking them up in terms of joules, not calories. I mean, calories is fine, but I mean, it's technically true, but we're not using them in here. And most of your problems are going to require the use of joules. Okay, so the question is, how much heat? That's what we're looking for. We're solving for Q. Okay. The specific heat is given. The mass given. And the change in temperature is there. One thing I want to remind you of, the change in temperature, your final number should always be positive. The reason for that is because we're just looking for a difference. For right now, we don't care in what direction. If you have a negative or positive delta T, it's because you're talking about directionality. It's either heating up or cooling down. All right? So just keep in mind, we're looking for a total change. So it would actually be, because this is negative, it's actually going to be 37 plus 8 for your delta T. So delta T is going to be 37 plus 8, because I got to get from negative 8 to 0, right? And then 37 more degrees. So what is that? 45 degrees Celsius. Okay? All right. So plug and chug. What you'll note is that Celsius cancels, grams cancel, you're left with joules. That's good because heat is in joules. And if you do the math, that should be your answer. Okay, I know these questions seem kind of complicated and long and crazy. They are. And this is what they're going to look like on a test. Also, not Tuesday like next week, not in a couple days Tuesday, but a week from that, like the Tuesday after Easter, I'm going to give you guys a seated in-class test. Okay? And it's only going to cover from what your last test ended on. All right? Because of time constraints, there will probably be no test corrections. In lieu of that, what I will probably do, it will not be multiple choice Scantron. It will be write out the work and do it that way. Because as I was telling a few other people who were asking me, if I give you, a question like this and I ask you to work it out, and let's say something required a balanced chemical equation, and you did every single thing correctly except balance that chemical equation, and therefore your work is wrong, you're going to get maybe a point or two off, as opposed to on a Scantron losing all 10 points per question. Okay? So I will figure out how I'm going to work that to make it, for your best interest. And then your final exam will be the last test you take in here. Okay? Questions?
And it's cumulative, right?
Yes. I think I'm required to do a cumulative. I think that's part of the
For chemistry.
Mm-hmm. Yeah, it's a departmental thing. So my other school I was required. It had to be cumulative. Okay. Any questions about this problem? Seems pretty straightforward. We gonna do another one? Let's do another one. I know you don't really want to, but let's do one anyway. Okay.
Is the final multiple choice?
No idea. I haven't even thought about it. Oh, sorry. Okay. So this is what another test question might look like. You first and foremost know that this is a heat capacity problem. Why? Because it says it right there in the first sentence. Okay? So you were told that she weighed it and measured its heat absorbed, how much heat it absorbed. And you knew what the temperatures were, the change in temperatures. And I want to know if it's actually gold. Or Sally, whatever. Okay? So what are you going to have to do to figure out if it's actually gold?
Find the heat capacity of gold.
Mm-mm. What are you going to do?
Find the heat capacity.
No.
Do you find the specific heat?
Yes. You have to find the specific heat. Why? Why the specific heat and not the heat capacity? Why? What about this problem tells you that it's not the heat capacity you're looking for, it's the specific heat you're looking for?
Temperature was raised until heat factor.
The specific heat is the only thing not given. We're given everything else.
Well, how do you know? I'm just not assuming you need to just look on a chart. Like the other problem, right? There's a very specific phrase that should tell you instantaneously you don't have to find the heat capacity. Say that again?
The heat absorbed.
Yes. The heat absorbed. It told you right here. It absorbed a certain amount of heat. What that means is that is the heat capacity. Okay? When it says it absorbs heat, that is Q. So you don't have to find that. We have Q. We have the mass. We have the two temperatures, so we can find delta T. We can solve for it, right? So in order to decide if it's truly gold, I have to find the specific heat and compare it to gold's specific heat. Okay? Each individual element has its own specific heat, just like each individual element has its own density, for example. Okay? So now I'm just going to plug and chug. So that's going to be equal to, what is it, 50. Just kidding. Okay. All right, so I don't know. Let's see. What is... Okay. So the specific heat for gold is 0.129 joules per grams degree Celsius. Is this really gold? Nope, it's not. Probably fool's gold, which everybody thinks is gold, but it's not. All right, now I want you to try one on your own. Okay. I'm telling you right now, I love this type of problem. No, this particular type of specific heat problem.
What about it?
I just like it. Okay, you guys work on it, and I'll come around in a minute. I'm just gonna write the answer really quickly. Answer up?
Yes.
You good?
Yes.
All right.
And there's another step.
Okay. You got it? Yeah. Okay, one out.
Oh my god.
Alright, so you basically are over. So if it is Q equals mass times specific, if it is Q equals mass times specific heat times delta T, right? We were given this, given this in the problem. Don't know this. We also know that if we were to rearrange this to solve for this, it's going to be delta T is going to equal Q over that. Okay? We also know delta T equals T final minus T initial. We were given that. And this, we just solve for. So then, solve for T final. Make sense? Okay.
Okay, I got it now.
I accidentally multiplied that one.
Uh-huh.
So that it. So
Yep.
that, so
Mhm.
yeah. I see
Yes.
it now.
I got 40.
You mixed up 2 and 0 for this 20.
I got 42.
Yeah,
it's 42.
Yeah, I might have inverted, but yeah. Yeah.
It's supposed to be 42.1.
I really care more about the process, and you guys understand the process, because now we're just going to throw a big old wrench in it, in all of this.
Oh, great.
Yeah, big old wrench I'm about to throw in it. How much time do we got?
Not enough.
Yeah, we do. Good try. You know what? We don't have to do these problems. You can do them on your own.
No.
I know how to do them. Okay. Actually. You guys can't even whisper quietly. Whisper quietly. I heard you too. This time. A lot of times it is just time, but I did hear you too. Quiet. Okay, I'm going to start you guys off with a hint. There's your hint. That's your equation. There's your wrench. I gave you the wrench. I'm just not going to tell you how to use it. Okay?